We have summarized the documents concerning the status, the facilities, and the activities of our radioactivity monitoring at the site of Fukushima Daiichi Nuclear Power Station. These documents will be described in several presentations. Today, we would like to explain the method of radioactivity measurement. Please show the slides. First, we would like to explain the difference between the radiation dose and radioactivity. Sometimes it is confusing even to us because there are various words which refer to radiation dose. Radiation dose means the particle beams or the electromagnetic waves which are emitted when so-called radioactive materials, in other words, the materials which emit radiation doses, reach a stable condition. Those that have the ability to ionize materials is expressly called radiation dose. On the other hand, radioactivity refers to these materials' ability to emit radiation. In some cases, radioactivity refers to the radioactive materials themselves. However, if we liken it to a sparkler, the fireball is the radioactive material, the radiation dose is the sparkles, and the radioactivity is the amount of sparkles. It is basically unclear whether there is a high probability that the radiation dose will be emitted. Still, the amount of the radiation dose emitted by the radioactive materials is indicated by the half-life period. The radioactive materials gradually turn into safe materials, emitting the radiation dose. The status of the change is estimated by the half-life period. The half-life period is the time needed to reduce by half the original ability of the material to emit the radiation dose. The half-life periods of the major materials are indicated on the right in small letters. They are 3.8 days for radon-222, approximately 30 years for cesium-137, which exists in the power station, approximately 1.3 billion years for potassium-40, and approximately 4.5 billion years for uranium-238. Next, please. Now we would like to explain the kinds of radiation doses which exist around us. We are exposed to radiation in such ways as through cosmic rays, foods, and from the ground. The radioactive materials are taken into our bodies via foods and respiration. For example, approximately 4,000 becquerels of potassium, a typical material which we intake, is absorbed by a Japanese body weighing 60 kilograms. As shown in the graph on the left, the world's average annual natural exposure dose is approximately 2.4 millisieverts. It is approximately 1.5 millisieverts in Japan. In the case of potassium-40, 4,000 becquerels, which is the amount normally present in the human body. Generally, 30 becquerels are contained in 1 kilogram of rice, as shown here. Next, please. I've just mentioned that the world's average annual natural exposure dose is approximately 2.4 millisieverts, and in Japan it is approximately 1.5 millisieverts. The natural exposure dose varies from place to place. This is mainly rocks or granite. The radiation dose varies depending on the amount of radioactivity contained in it. In the Kanto district, the radiation dose is comparatively low because there is a layer of loam. It is 0.81 millisieverts per year in Kanagawa. On the other hand, in the Kansai district, the west part of Japan, there is a lot of granite. Therefore, the radiation dose is 1.10 millisieverts per year in Gifu. In looking at other areas in the world, in the Guarapari Desert in Brazil, the annual exposure dose is 10 millisieverts per year. I will explain in the next slide about the generation mechanism of radioactive materials. These are the radioactive materials which are produced by nuclear fission of uranium-235 and should be controlled at power stations. They are the nuclides such as iodine and cesium, which are important in order to control gamma ray exposure. The nuclides which are important in order to control beta rays are strontium and tritium, for example. There are also alpha nuclides such as plutonium, americium, and curium, or rare gases such as xenon and krypton. The basic mechanism of nuclear fission is described in the chart. When neutrons are absorbed in uranium-235, unstable material uranium-236 is generated. Because this material is unstable, iodine 131, yttrium 103, and several neutrons are produced. We call it a chain reaction when the neutrons successively strike the next 235. When this continues, the phenomenon is called criticality. Materials such as iodine, cesium, and strontium are generated this way, but on the other hand, plutonium, americium, and curium turn into transuranium elements without nuclear fission when neutrons strike uranium-238. Tritium is generated when neutrons are absorbed in the heavy water layer contained in water. In a reactor, a lot of water is stored as coolant. Tritium is generated when hydrogen strikes the slightly heavy water layer contained in the water. Next, please. There are 4 kinds of radioactive doses, which are alpha rays, beta rays, gamma rays, and neutron rays. We measure mainly the gamma rays, considering the influence its exposure has on human bodies. However, the beta ray and alpha ray can also cause severe problems in controlling the exposure dose. Therefore, we analyze the dust and have the workers wear full face masks. The ability of each ray to penetrate through to the materials is shown in the illustration on the right. The alpha ray can easily be shielded by paper. The beta ray can penetrate through paper, but not aluminum foil. The gamma ray has to be shielded with lead or thick iron plates. The neutron ray does not have a charge, which means it cannot be shielded with paper, aluminum foil, or lead. It can be shielded with materials consisting of comparatively light atoms such as water or concrete. By the way, regarding the range, the distance those rays reach, alpha ray with 2 mega-electron-volts of energy reaches 0.01 meters, or about 1 centimeter, and the beta ray's reach is only about 8.5 meters. Furthermore, we will explain the unit of radiation and radioactivity. First of all, the degree of radioactivity is indicated with the becquerel unit. This shows how much radiation is emitted per second. That is, the number of atoms of decay per second. For example, in the case of a floor, when we show the radioactivity of radioactive materials attached to things on the floor, the degree of radioactivity is expressed by becquerels per square centimeters. And in the case of air or water, the degree of the radioactivity is expressed by becquerels per square meters. And with respect to the radiation in consideration of its impact on human bodies, we use sieverts. The sievert is a big scale unit, and therefore we usually use the units of millisievert or microsievert. And for an hourly basis, millisieverts per hour or microsieverts per hour. We have so far explained that counts per minute, that is the unit that measures radiation, and sieverts are hard to exchange with each other. But basically, counts per minute means the amount of radiation that comes in a detector per the unit time. With respect to the lower right picture, not all the radiation that is emitted from the radioactive materials is counted by a detector. In some cases, radiation does not come into the detector, and in other cases, radiation enters but just passes through. When this happens, it does not produce a reaction in the detector. As shown in these examples, we can see that it is difficult to convert counts per minute, the number of radiation detected in the unit time, the number of becquerels, and the number of sieverts. On page 7, we show how we convert the unit in such cases. First of all, we basically compare the radiation that is actually detected with the standard radiation source, a source of which the number of becquerels is known. After that, we consider to what extent the counting rate matches and use A and X as conversion constants. Then, with respect to the assumption from becquerels per square centimeters to microsieverts per hour, as shown in the picture on the right, we assume to some degree the location of the detector and the shape of the surface with the radioactivity, and we count with the detector and convert the number of becquerels. Take an example in the case of cesium-137. If you take measurements at the detector's height of 1 meter for the contaminated area of 40 centimeters and detect 13,000 counts per minute, the result is approximately 0.04 microsieverts per hour in the conversion constant. This is, of course, dependent on the type of radioactive materials, the contamination area, and the distance. Next, please. We will now explain how we measure the radiation in plants.